You probably think a container ship is at its most dangerous when it is facing violent storms or waves as tall as buildings in the middle of the ocean. In reality, the easiest part of an entire journey spanning thousands of kilometers to go wrong is in the final few minutes when it enters the port. Out on the open sea, it is a giant that dominates everything. But near the shore, it becomes clumsy and has to hand the hardest part over to vessels hundreds of times smaller than itself. Why does the biggest thing in the ocean become almost helpless at the exact moment when precision matters most? The answer is not in size, but in inertia, in the limits of the steering system, and in a machine designed for one purpose only: controlling chaos in a tight space. Welcome to Everyday Things Explained. The problem is not mass, but the loss of steering. An ultra-large container ship can weigh up to 200,000 tons. Out at sea, that size is an absolute advantage. It is stable and fuel-efficient because its inertia is so good. But a port is a completely different environment, tighter, slower, and with an acceptable margin of error measured only in centimeters. This is where a physical gap appears. A ship's rudder only works effectively when enough water is flowing past it. When the ship slows down to dock, at a speed roughly equal to a walking person, the flow of water across the rudder becomes too weak. That means the ship still has all of its enormous mass. It still has the inertia of drifting, but its steering wheel has already stopped working. At that moment, the ship no longer behaves like a vehicle being driven more slowly. It behaves like a gigantic block of steel drifting forward, no longer obeying the person in control. Wins through geometry, not through muscle. A tugboat is far smaller than the mothership, but it does not need to be the same size to control that giant. Its strength is measured by bollard pull, the actual pulling force it can generate when tied to a fixed point and running at full power. Imagine a seesaw in a park. A small child can still lift an adult high into the air, as long as the child sits all the way at the end of the beam, while the adult sits close to the pivot in the middle. Distance is what creates power in the world of physics. And that is exactly the principle a tugboat uses. By applying force at the bow or stern of the ship, the points farthest from the center of mass, it creates an enormous torque capable of rotating the vessel. Modern tugboats, in particular, use the Z-drive system. Their propellers can rotate a full 360 degrees, allowing them to push sideways, spin in place, or redirect force instantly. It is a machine optimized to the extreme for one single mission: controlling the direction of movement in a confined space. The critical job is braking, not pushing. Our intuition usually tells us that tugboats are there to pull ships along or push them into the berth. But in the final stage, their most vital role is actually to slow the ship down. A ship weighing hundreds of thousands of tons, even when moving very slowly, still carries enormous kinetic energy. If it hits the dock even slightly faster than planned, the impact can devastate the pier. At that point, the tugboat acts like an active shock absorber, pressing against the ship's direction of drift, turning the approach into a gentle lean instead of a destructive collision. Never confuse slow with safe. With gigantic objects, low speed does not erase inertia. It only makes the risk less visible right up until the collision happens. The system of control and pragmatism. A successful docking is a carefully choreographed dance. The harbor pilot coordinates 2 to 4 tugboats over radio, calculating the wind direction and the current second by second. One small mistake in coordination can lead to disaster, like the Ever Given grounding in the Suez Canal, which paralyzed global trade. So why do we not design container ships to be more agile? Why not install extremely powerful bow thrusters so they can dock by themselves? The answer is the pragmatism of industrial inertia. Adding more complex maneuvering systems would reduce cargo space, increase maintenance costs, and consume more fuel over long voyages, the shipping industry chose a different path. Optimize the ship to travel straight as efficiently as possible and leave the delicate work to the support system at the port. It is cheaper, safer, and more specialized. And it proves something important. Sometimes the best solution is not to make yourself perfect, but to build a perfect support system around you. So the next time you see a tiny tugboat looking completely outmatched beside a giant vessel, remember this: in the most important few minutes of the entire journey, that little ant is the most powerful thing in the ocean. But did you know, tugboats are not the only things protecting a port? Even the concrete walls that ships lean against are designed to survive in a way you probably would not expect. Have you ever wondered why a pier is never built as one completely solid, rigid block of concrete? We will unravel the mystery of concrete flexibility in the next episode. Thank you for watching. I am your partner here at Everyday Things Explained. Do not forget to leave a comment about the smallest but most powerful thing you have ever seen. Goodbye.